Hello, and welcome to day 27 of learning ML from chatgpt. So let's get started. So in yesterday's lesson, we looked at natural language processing with things like BERT and GPT. So BERT is a pre-trained model here that we can use different token IDs and, input IDs, I think. Well, first of all, we got to tokenizer, which converts them to token IDs, and then attention mass are which input IDs are relevant. Okay, so let's move on to day 27. Let's see what we've got in store for today. Okay, so advanced computer vision, object detection, segmentation, YOLO, mask art, so recurrent CNN, I'm pretty sure that is. Recurrent convolutional neural networks, so CNNs are the ones with the kernels and the filters, where you have like, I forgot the name of them, but you basically loads of different small, they're kind of like data frames in itself, but like each filter, so a kernel, so you have a 3x3 kernel, goes over the pixels, and it tries to find relationships, and it keeps on going down the image, and different filters are randomly, like they got different weights type of thing, to start off, so then they can figure out different patterns in the data. I think that's because I think it was like 20 days ago in this course that we learned about CNNs. So if we can paste the text in here, we should be able to start. If not, I'll have to refresh this page. Okay. Let's see. Okay, this should be it. Okay, nice. So please give me day 27's lesson. Okay. Yeah, in the past few days it's been bugging a bit because there we go. It should work this time. But normally it just doesn't give a response, and then it has the like thumbs up, thumbs down, and then the like circular arrows. Okay, it's done the first time this day. Okay, advanced computer vision. Concepts: object detection, identifying and locating objects in an image, drawing bounding boxes around them. Popular for applications like autonomous driving, security systems, etc. Segmentation, categorizing every pixel of an image into different classes or objects, e.g. background versus object. There are two main types. Semantic segmentation classifies pixels into categories, sky, road, or car. Instance segmentation identifies individual instances of objects, detecting each person in detecting each person in an image separately. YOLO, you only look once, a real-time object detection model that processes the entire image in a single forward pass. It's extremely fast compared to the other detection models. Mask RCNN, an extension of faster RCNN for object detection and instance segmentation. It not only provides bounding boxes but also pixel level masks of detected objects. So code examples: YOLO object detection with pre-trained models. This example uses a pre-trained YOLO v3 model to perform object detection in images. Okay, and the assignment is going to be use a pre-trained YOLO model to detect objects in an image of your choice. You can use images from datasets such as Coco or real-world images. You capture, visualize the bounding boxes and labels of data, detected objects on the image. Okay, then it gives us some resources. So I'm just going to read through this code. So we're importing CV2. I'm not quite sure what that is, but assume that's going to be where we get the YOLO pre-trained model. Okay, then we have NumPy, opening Coco names, which is just, I assume, a bunch of images that we can use for testing, and layer names, alpha layers. Okay, this is all a bit of boilerplate for this. Image.png, this is what we want to actually do, and then we're going to get confidence. Okay, and then so I'm just going to leave it like this because I don't think the code will change, and it's just pretty boilerplate, so it's easy to copy to and from. Okay, so YOLO is the pre-trained model. You only look once, which is very fast. Okay, so we don't actually have the YOLO V. Anyway, what we can do then is we can go back to the original lesson, which is CNNs. If I go back, okay, so yeah, so we can have a look at these CNNs. Okay, advanced. Oh, wait, we can go back to this first. Oh yeah, they were called feature maps. Okay. Let's see if we can get to the convolutional neural networks. Okay, the convolutional neural network is a type of deep learning model commonly used for image classification, object detection, and similar tests involving grid-like data. CNNs are particularly effective at capturing spatial hierarchies in images due to their specialized layers, convolutional layers, and pooling layers. Okay, convolutional layers. These layers are filters or kernels that scan over the input image, applying convolutional operations to extract features like edges, textures, and patterns. The kernel moves over the input image and performs element-wise multiplication, producing a feature map. Okay, so just going back, so we have these filters, which have a kernel that like slide over the image, and then it performs element-wise multiplication to create a feature map. Okay, so then we have pooling layers. Pooling layers reduce the dimensionality of feature maps, making the model more efficient and less sensitive to minor variations. Common types include max pooling, average pooling. So activation function ReLU, often used after each convolution to introduce non-linearity. Fully connected layers. After the convolution on pooling layers, the data is flattened and passed through fully connected layers, which makes the final classification decisions. CNN architecture. So we have an input image which accepts image data, typically represented as a 3D tensor. Height, width, and depth. Convolutional layers learn local features from the input. Pooling layers downsample the data to reduce complexity, and fully connected layers combine features and predict the output. So here we use CFAR10, which, if I remember correctly, it has like toad, lorry, boat, and several other things it detects. Okay, so first we import the libraries, then we have X-train, Y-train. This divided by 255. Make sure that the pixel. So with RGB you can have like 255, 255, 255, and that's the max for the RGB. The red, green, blue components of it, and then if you convert it to a range, this is called normalization, which was one of the first lessons. So be sure to check that out. So we're converting it in a range 0 to 1 to make it easier. Build the CNN model. The model consists of multiple convolutional layers, followed by pooling, then a fully connected layer. So 32 layers, 3 over 3 kernel. Okay, so the input is 32 by 32 by 3. Then this is our kernel. So we're having 3 by 3, so 9 pixels in total. We're going to be sliding over this shape, so we can pick out features like edges and textures. Okay, then we have a max pooling layer to reduce spatial dimensions, and then we have a second convolutional layer, 64 filters. So remember, we're turning each one of them into a feature map using element-wise multiplication. We have another convolution, 64 filters, and then a third one. And then we're going to flatten it, and then add a dense layer, the final one, 64, because we just had 64 filters. ReLU, and then we can have one last. We can use softmax, because this gives a probability for every one of the output neurons of whether that's the most likely or not. Compile the model. We use the Adam optimizer categorical entropy, since this is a multi-class classification problem, and accuracy as a metric. Train the model, train the CFAR. Model in the CFAR10 training set for 10 epochs with a batch size of 64. Okay, so we're going to fit it X-train, Y-train, epochs 10, batch size 64. We're going to have the loss. So task, train the model at least 70%. Yeah, I think that's what we did. So cleans what 2D convolutional layer with 32 filters. Okay, we'll read this quickly. So a kernel, also known as filter, is a small matrix, usually 2D, used to detect specific features in an image. It is size 3x3, 5x5, and it slides, convolves over the input image, performing element-wise multiplication between the kernel and the input image at every position. The resulting values form a feature map. So, okay, and the input image. So, for example, with a 303 kernel, it might look like this. This kernel detects vertical edges in an image. Filter. A filter is essentially another name for a kernel. However, when we say 32 filters, we mean a layer that has 32 unique kernels. So each filter will scan over the image to detect different types of features, such as edges, textures, or patterns. In the context of CNNs, we say 2D convolutional layer with 32 filters and a kernel size 303 means the CNN layer has 32 separate 303 matrices, kernels. Each kernel size of the image applying convolution, multiplying and summing up values every position. This operation creates 32 separate feature maps, each representing a different feature detected by the corresponding kernel. This is a more abstract and feature representation of the input image that the network can use to make predictions. So now please explain what different layers where it does the data and how do we combine all those features that are made. Okay, let's see. So we have these. Okay, just what we saw before. So this applies 32 filters. The filters will scan over the image to detect various features, edges, the relay activation shape is applied to each pixel in the feature maps, turning all negative values to 0 and keeping positive values. This introduces non-linearity, helping the network learn complex patterns. This is the input shape, meaning each images of size 32 by 32 pixels and 3 channels. This layer reduces the size. And this is another convolutional layer similar to the first one, but with 64 filters. This means that it will extract 64 new feature maps based on the already transformed pooled input from the previous layer again. Okay, so in this line, you see that 64 new feature maps will be created. So are feature maps just 3x3 or are they the full image? In the line, as 64 feature maps created are not just 3x3. Let me clarify this. Okay, so filter kernel. The 3x3 refers to the size of the kernel. Filter. Just hold a minute, sir. Okay, size of the filter or kernel, which is a small grid that slides over the entire input image. Feature maps. They're the output of the convolutional operation. Each feature map represents the result of applying a specific filter. Okay, so feature map to a specific filter, then it with the element-wise multiplication. So if you apply 64 filters, each of size 2x3 to an input image, or the output generates a full feature map, which is the size of the input image. 64 filters to an input image, or the output of the previous layer. Each filter generates a full feature map, which is the size of the input image. Okay. Yeah. So if the input to the convolution layer is an image of size 32 by 32, each of the 64 features will slide over the image, convolving it, and the result will be 64 different 32 by 32 feature maps, one for each filter. If the input is smaller due to previous operations like pooling, say it's 16 by 16, the convolution will produce 64 16 by 16 feature maps. Okay, another question. How are the 64 feature maps here different? Isn't the same operation being performed on them? Or is it that after every feature map is created, the weights and bias change? Great question. Each of the 64 feature maps is generated different by a different filter, also called a kernel. Each filter has its own set of weights and biases, so while the same operation convolution is performed for each feature map, the filters are different, leading to different feature maps. Here's a breakdown. Okay, each of the 64 filters in the layer has its own unique weights, so that's why we're having 64 and they're not just the same. But the weights are initialized differently and are updated separately during training. Convolution process, each filter is still across the input image or the previous layer's feature maps. The filter performs a convolution operation, dot product of the filter's weights with the image patch it slides over. This produces a new feature map corresponding to that filter, which highlights specific patterns like edges, textures, or shapes. Weights and biases. Each filter has its own independent weights and biases, so after each feature map is created, it reflects the specific characteristics the filter has learned to detect. These weights and biases are learned during the training process. As training progresses, each filter learns to detect different types of features or patterns, e.g. edges, textures, etc. Why they're different? Even though the operation, convolution, is the same, the weights and biases are different for each of the 64 filters. As a result, each filter detects different patterns in the input, producing 64 distinct feature maps. One filter might detect horizontal edges, another might detect vertical edges, while others may detect corners or specific features. Okay, wait, let me just read. So, we have 64, times the original. Okay, in the first, you start with the input image. After, okay, so yeah, so after the first one, we had a 32 by 32 shape. Let me see. Yeah, and we had 32 filters. When you add the second, it takes the output of the previous layer, which is its input. Each of the 64 filters, across all, and producing. Oh yeah, this is the thing. It's quite confusing. It only produces 64 new feature maps. Let me see. Okay, each convolution operates on all the input feature maps at once, but it produces only one feature map per filter. Here's how it works. Wait, all of the input features maps at once. It produces only one. Oh, okay. It's because we're producing one for 32 for the image and just one for each of the other ones, the already feature maps. I think. Let's assume we have 32 input features previously from now apply 64 filters. How filters work. Each of the 64 filters in this convolutional 2D layers are 3x3 in spatial dimensions, but in depth dimension, the input will span all 32. Ah, I see. Oh, this is why. Okay, so just to explain it, so what we have is we have 32 feature maps, and it's the same size that we had before. So say we have our image here, then we have all the other images. They're in the third dimension, and they go back here. And then what our kernel does, it takes like the 3-dimensional shape out of there, and then we can do that 64 times, and that produces 64. And then so the more convolutional 2D layers we have, like the better output will be, but like the even more complex of a shape it will get, because we'll have a 3D one, then with 3D little the other kernels, like say we had like 2 layers here, like this front layer would have a pixel, and this pixel would also be 3 but this pixel wouldn't be 1D, it would be 2D. So I'm not sure if that's called 4D. I don't think it is. If there were, which imply multiple feature maps, it's not. Okay. Yeah, okay, I get it now. Yeah. So I think that'll be all for today's lesson. So thank you for watching, and I'll see you in the next video. Goodbye. So just to recap about today's lesson though, we learnt about like fast CNNs using YOLO. You only look once, which is like pre-trained, and it's very fast for image detection, like real time and like images and self-driving cars. So yeah, thank you for watching, and see you in the next video. Goodbye.